It's all contained in here, and then that sends the information to our STM board, which then processes it, and we display it upon our laptop, which will be attached to the top of the actual glove box. So what we did is we have everything attached down. So we have like the computer, the charging cable. We have the power strip, the surge protector, the kill switch right there attached. It's all attached to the inside, so you can reach in, kill it at any point. And we have all the ports attached.
You need to speak up.
I'm sorry. Okay. So also we have the tag, which is in our suitcase right over there. Truman, do you want to grab that?
Yeah, sure.
Which is, it's in a styrofoam ball because that was like our projection unit. We wanted to store it within an object to see how it would transmit to the antennas and to our device. So we have it within there where it's going to be picked up by the actual antennas or by the readers that are within our lab, and be transmitted to our board where we'll project it and track its real-time location, like on our computer on the GUI displays and stuff.
So you said these are going to be attached to what? With Velcro. And then what about
the cords?
The cords will be on.
What was that about the cords?
Oh, they were going to be run under the floor, or underneath there. So.
And then is this going to be? That'll be not. Yeah, they would take it off. So. Okay.
And we're going to kind of be your main presenters for the day. So our project is called Navi, which stands for Navigation in 3 Axes. And so we were kind of looking at a device where Don Pettit created a stabilizer using 3 CD players. And so we decided to take his idea further by creating a more high-tech version. So what we did is we created the same device using 3 motors and then using acrylic discs to kind of act as like the counterweights, much as a CD would be in a CD player. The code to the ESCs to control the motors. And so this way, we'll be able to set the device, much like an astronaut would, then be able to start it up on the phone and have it stay there and not move away, because that's an issue in space. When we set something down here, we expect it to stay there. That doesn't happen. When you're in space, the last moment you touch it, that's the last force it has, and it'll float away.
Okay, we're Warren Tech. We're doing the carbon dioxide scrubber. And how we came up with the idea was the NASA Reduced Gravity Office and NASA Education put out a document that had proof. And on page, I believe it was 17, Dottie Lindencalf, one of the astronauts, said how when they're in a large space together or when they close into their sleeping quarters for 6 to 8 hours, the carbon dioxide builds up and encases them in a bubble of their own carbon dioxide. That can create headaches, it can create nausea, and you can get really sick from that. So ours is kind of meant to scrub that carbon dioxide out of the air so they can gather in one place and talk to NASA all on the TV and Skype, or they can sleep and get a great night's rest and wake up and feel refreshed and not sick. A U-shaped channel. This U-shaped channel, the air gets pulled in through this 5-volt computer fan, and it comes in this side, circles around, and goes out the other side. Then it's all controlled by this NESI board. Currently, we only have the fan running off of the NESI board. Our carbon dioxide sensors are...
So they're all in these little tea bags, and so if you break them down into really tiny particles, they can actually be a carcinogenic material. But if you put it in the tea bags, it'll make sure that everything is still contained within there and still let all of the atoms flow through it. So they actually have different pore sizes, so regular oxygen can fit through there. But when you have a carbon atom put on there to oxygen, it actually gets stuck inside of the pores on the molecular sieve. And so that also catches water, which isn't necessarily a benefit to our program, just a little tidbit of information there.
And it goes straight through, instead of the U shape, it goes right in from this side and out through the fan. And the zeolite packets, instead of this design that they have, are more square like this, the actual size of the tea bag. And they fit inside of these little cartridges that slide out. And there's 3 different cartridges inside of this device. Okay.
My name's Austin Casey. I'm going to do most of the speaking here. This is the Vortex Pump. Vortex is not an acronym, it's just Vortex that you think of. What this pump is designed to mitigate is on the thermal control system on the ISS. They currently use centrifugal pumps, and they're called can pumps is what they call them. And the problem with those is that they tend to break down often. And what this is supposed to do is just a simpler design. There's one moving part on it, and it's less likely to break down. But there's also some fun things to test in here too. Inside of here, there is a round plunger, but the plunger has rubber reeds on it, and they will open and close depending on the direction. Close to push the water throughout the system, and they will open when it's pulling back to reset itself. But when that happens, it'll spin the water into a vortex. And sorry. And what that's the idea with that is if you ever fill a 2-liter bottle with water and then you spin it around into a vortex, the water will come out a lot faster. So what we're looking to see is if that happens with this and we get the vortex, it might make it easier for the water to come out and go through the system. Then we have bulkheads on either side, and that will go through this this vinyl tubing into this flow meter right here. We'll have a GoPro monitoring the flow meter throughout the entire flight, so we can review the data later. And then all of this is powered by this electric actuator that runs off of a 12-volt DC at max 5 amps when it's fully pushing hard. That is all powered by this. This is an AC to DC converter that will plug into that, and that will run through here into our electronics box. Inside of here we have a relay that will be switched by an Arduino.
Good morning, ladies and gentlemen. My name is John Korber. This is Wilton Springer, Cam Moore, and SO, and that's Stephanie Salerno. We are from Jackson Hole High School. Our experiment this year is titled New Docking Mechanisms Utilizing Solenoids and Quantum Pinning. It's the first of a 4-year experiment sequence that we planned, by the end of which we hope to have a model of basically an automatic docking mechanism for spacecraft. This year, we don't have the quantum pinning. We're focusing on the electromagnetics portion of it with our solenoid. In our experiment, we've got we have a solenoid powered by a current control power supply, which is in turn plugged into an outlet timer. This end of the experiment will be used for both parts of the flight. It's divided into two different sets of data that we collect. The first of which we will use the force probe on the left side. Attached to the force probe is a guide string. You're right. Attached to the force probe is a guide string and what I call a force string. The guide string basically just constrains a small length of magnets to the effective range of our solenoid. Closer to the probe, which basically just advances
North Carolina School of Science and Math. Right now, I'm working on a parasitic pump. So from space, moving parts often break, so big problem. NASA's called for a new development. So we're making use of nitinol wire. Nitinol wire is shape memory wire. When you heat it up or apply voltage, it will change shape. And when it goes back down, it'll go back to its original shape. So we have a series of nitinol wire stretched across the tube in here. It's kind of hard to see. If you want to look at it, we can do one at a time, but I don't think it's convenient for all 25 of you. Essentially, if you can imagine my arm as the tubing, we have nitinol wire stretched across like this. So hooked up to the Arduino board, MOSFETs, and a set of batteries. The Arduino board powers the MOSFETs. The batteries will activate for each specific wire. The specific wire will then contract over the tubing, causing water to flow forward. Because it's set up, we're going basically 2 wires at once. As one wire goes down, the wire behind it will just be coming up. So that means we're going to be limiting backflow. We're going to be hoping for a net forward flow going through this clear tubing. We have highly compressible tubing in there, so it works pretty well. It takes about 64 seconds to cycle through the entire thing. And yeah, any questions? See it function, you can kind of look in here. I can turn it on for you if you'd like.
No, that's all right, but I know it's going to be safe.
Then on the back, we only have the compression on one side. On the back, we just have the tubing coming up.
Let's move in the flow.
Just tightening the wires, is that what it's doing? So this is going to be filled with water? Some fluid? What kind of fluid?
The tubing will be filled with water. We're going to be putting a little soap and red dye in it so that we can see essentially just bubbles moving here. It'll be pretty clear.
Modulated method of blood temperature test, but we will be bringing that next year. This year we just have an EKG connected to LabQuest, and we're going to be collecting data by attaching it to our wrist and forearm.
We're just gonna do simple movements, like laying down, sitting, standing, running. Very simple movements that astronauts use.
So this way we can compare the effects of microgravity and under standard conditions and on the circulatory system in microgravity. So kind of seeing what happens and the different changes, seeing if you get more excited or how much less excited you get and how these different actions can affect the circulatory system.
So shouldn't that have IRB approval?
So we're Tri-County, and we designed this zero gravity mass scale. So the way this works is we have two force sensors on here, one right here and one right here, and they're actually donated from Mark 10, which is lovely. And what we do is we have a known and an unknown mass. So on one side we have the known, one side the unknown, and we can actually spin the center column to create force, and we read the force and find the ratio between the known and the unknown mass and use that to figure out the unknown using force equals mass times acceleration. As you see here, spinning, lovely.
Our experiment's right here. Hello, my name is Estelle Velasquez.
I'm Brandon Is.
Rosa, Joanna Torres, Alondra Martinez.
I'm sorry.
Alondra Martinez.
So our project here is our CAR system, which is our controlled atmosphere room simulator. This chamber right here will be able to test the stratification of 3 gases.
So it's CO2, carbon dioxide, oxygen, and nitrogen.
So what we're actually trying out here is trying to keep apples in space longer and fresh apples longer in space. So this is one of the methods that you can use to keep apples longer. We know that astronauts love apples, and coming from Washington, apples is a big thing is a big industry. So go Washington.
And how we saw the problem was that an astronaut blogged about how delightful a fresh apple would be if it would come weekly or if it would be just fresh, and so that's why we came up with the cars.
Not only for the safety of it, but also if it will work.
I don't know if you guys ever known that apples, they live and breathe just like us too. And you guys heard of the saying, one bad apple make all the rest bad. Well, that's how it is. What we're trying to do is, put them basically in like a coma light, so that they'll slow down the breathing and the respiration, and so they won't give off ethylene gas, and so all the other apples won't get rotten.
So how it goes is you stop respiration, you stop the production of ethylene. Ethylene is a chemical that actually can speed up the process of ripening.